stuff. And then afterwards we'll have a Kahoot, and we'll have the first winner get a good prize of Minecraft, trust. And then afterwards we'll give you guys a challenge problem, and you guys can try and work it out in breakout rooms, and then we'll release the answers later tonight. So on to Zac now, our guest speaker.
Okay, all right, hello. I think, great. Oh no, hang on, finally. Good, it wasn't picking up my OBS before. So I'm thinking that Zoom is working now. Is this working? Can we see? I've got the...
We can see.
Okay, good. I've got the Zoom chat open on the side over here. So I'll try to keep up with that, assuming it works. And we'll not try and leak my Signal chat, I guess. And we'll get started. So I believe the vague plan for us is to just do a few Mips programming exercises. Yes, hello, everyone. And then let me put this over here, actually, so I make sure I'm not doing anything dumb. Cool. And then I think I'm going to run a Kahoot that has very nicely been made for me. And after doing a few exercises, and then we'll see how we go. Muted, by the way. Am I?
No, I can hear you.
Okay, maybe you might need to check some audio settings. All right. So first of all, where should we do this? I guess we'll do, this is Mipstifying, or however you spell that. Okay, cool. So because we're sort of assuming that you've been to, a fair few tutorials, and you've been playing around with Mips for a while, I'm not going to start sort of at the very beginning of things per se. So we'll probably just do a few translation exercises. So we'll probably start off with doing something a little bit simple, like an if statement in C. We'll translate that across to Mips. Then we'll just move on to a slightly bigger example. We'll probably get through about 3 of them in 40 or 45 minutes or so, hopefully. So we'll see how we go. So let me make a sort of vague thing of a C file over here. All right. And probably the first thing we want to start with, just to keep life easy for us, is if statements. We'll try and move on to say maybe a couple types of loops or something, and then we'll end off with some sort of like functions example or something. So all a bit wishy-washy. If people have ideas like, oh, I'd like to see this thing thrown in, blah, blah, I don't tend to plan my things out to the T. I usually just run in and sort of work it out there. So feel free to like throw in ideas if you want to see them, and I'll do my best to integrate it in. Start by making a snake program, no ulterior motive. Right, so let me make the full assignment first, and then we'll run through the translation of that. Yeah, lots of fans of that idea. Okay, so simple if statements. I think when Shrey did a little Mips workshop, he made a little like checker if something is even or something along those lines. Maybe let's make a little checker, just a very original example. Let's check if it's divisible by 3 or something like that. So I'll write int input scanf into our input some sort of number. And then we go if our input mod 3 is equal to 0, right? That's how we check if something is divisible by 3, or, where whatever your n is over here. If input mod 3 is 0, we'll printf your number is, no, not even, is divisible by 3. Like that. And then otherwise, let's say your number is not divisible by 3. Boo, like that. Okay, I've made life very hard for myself because I never memorized the thing to grab this onto my X clip, so that'll be fun in a second. And now we have a little C program. So let's just try it out to make sure it's doing what we want. So clang-if.c if, right, let's say I give it the number 42. 42, yeah, it should be divisible by 3. 43 isn't, 44 isn't, and then 45 should be. Okay, so it looks like it's doing roughly what we want. And now we want to translate this across to Mips. Is this plagiarism? Actually, you credited me, so it's fine. No, it's not plagiarism because this is a completely original idea. 3 is an entirely different number from 2. So I think you'll find it's actually perfectly fine. All right. So here's how I like to translate my MIPS across. I like to sort of put my C code right on this side, and then my MIPS right here, and just do them make sure they're both open for me. I use a terminal windowing painting manager to do that. You could literally just open 2 terminals and put one, on this side here and one on that side there. Or you could go to Shrey's Xmonad workshop, or watch the recording rather, and have a whole thing and ruin the rest of your life. So I'm just going to do it like this. And I'm going to make if.s as our assembly file. So the first thing to usually start with in our MIPS code is a main label, which is roughly analogous to our main function. When Spim is executing our file, we'll execute it in a little bit once we've got some code ready to go. It will jump and link to our main function. So it'll call this by jumping to our label. And it also sets a return address register to tell us where to go back to when our function's finished. So I'll write that now, JRRA, which says jump to the address stored in a register, where that register is $RA, standing for return address. So essentially what this is saying is my main is just going to immediately return, right? It's not going to do anything fancy. Literally, this line translates to this C code here. And again, this $RA is going to be set by Spim when it actually calls when it runs our main code, when it calls main. So if I go on, assuming I was on CSE, I'd write 1521 spim -f if.s. I'm on my own computer, so I have Spim installed already. So I'll just write spim -f. You won't see this loaded exceptions line on CSE. If you run Spim at home, you'll see this kind of line over here. You can just ignore it, but you can see the program essentially just does nothing and returns, which is to be expected so far. Let me just have a quick look. Workshop, an IP address. Oh yeah, that's definitely a public IP. Tmux, great, called out. The software is called Tux. I think you mean Tmux. Yeah, cool. All right. So let's start translating some MIPS across. So we've got main. The first thing we're going to need to do is to get some input. Now, I know how to do this because I've had to type this about 100 odd times this term already. So it's sort of baked into my head, but let's say we don't know how to do this sort of on the fly. How do I know, what sort of sequence of operations to do to get some input? Usually your best bet is by going to the course website. So CGI, CSE, UNSW, tilde CS152121T2. And this section right here is going to be an absolute lifesaver. You can see the bright light of the course website is lit me up. But this is going to be an absolute lifesaver. Make sure you know about this documentation, because a lot of the rest of this stuff isn't that good. Whereas this page here is super handy and has almost everything you want. So if I want to read a value, I'm looking in system services, reading values. Let me go to system services. And this is what we'd call a bunch of system calls, which is our instructions. We don't have like a scanf instruction or a printf instruction or a read file instruction, because those are really big ideas that the operating system needs to handle. They're not sort of these low-level instructions that our CPU has. So we use these system calls to say, hey, operating system, please do something for me, right? And in this case, the do something will be read in an integer in the terminal and then give it to me somehow. So if I scroll down to reading values and I see read int here, it says it'll read a integer from the console into the register v0. How do I call this system call? It says set v0 to be equal to this value over here, 5. Then we'll execute the syscall. There's no arguments to this function here, to this system call rather here. Excuse me. So we can just make the system call straight away. And it says that it will place that value that it read in the v0 register afterwards. So that's where we'll expect it out. All right, back down to like normal skin tone over here now. So we said that the syscall was 5. So I'm going to execute a load immediate instruction, which means load a actual value I'm about to type into the code into my register v0. So this will put the value 5 into v0 here. I'd like to leave myself a comment. So I remember in future that syscall5 means read int. I'll execute the syscall, which is roughly analogous to the line scanf %d ref input over here like that. You know, it's vaguely doing what this line is here. And then I could just know, well, after this system call, my inputted number is going to be in V0, but often you'll end up using V0 for other things later. Like if you want to do more system calls, you know, we'll have to store the system call number in V0 and we'll lose that number that we needed. So the first thing I'm actually going to do is use a move instruction, which is a terrible name for an instruction. Wherever I say the word move, imagine the word copy in your head, because it will copy the value in V0, which should be the thing that was just read in, into the register T0 here, where I'll use it for like later convenience. YouTube, cool, yes, awesome. All right, so since I'm going to end up using V0 again for other things, probably best to just copy it straight away into another register where I'm not planning to put anything else. Okay, so now we're sort of up to this part in our code here. We've got our input, which is now going to live in T0 here. We need to check if it's divisible by 3. And then we need to, you know, work on this if condition here. So do this printing and stuff like that. I also have noticed that this return here just says return. It doesn't say return 0. The reason is if you were at the lecture earlier today, we now know that the V0 register is also, not only is it used for specifying which system call you want, not only is it used for giving like a return value from a system call when after you call it, it's also used generally to talk about the value you're returning from a function. So if I want to return the value 0 from main, then I have to put the value 0 in the return value register, in this case, which is a V0. So I'll say V0 0 and then return. So this is analogous now to saying return 0. So this line's done. These lines are done here. I just have to do our if statements over here now. All right. Now, how do I work on this condition if input mod 3 is equal to 0? Well, you know, we can check equal to 0. There's some Mips instructions for that. But input mod 3, let's say, I don't know how to do that in assembly. Back to our documentation and back to like my face being completely blinding. If you look in instructions and just have a scroll through, I don't think you'll reach any point in this course where there's some coursework you have to do. You think, I need this instruction to do this thing, and you won't be able to find it in this list. So if I'm like scrolling down, there we go. That looks like modulus. And it says rem is remainder after word division, and this is remainder after unsigned word division. I don't care about, my value is technically signed in this one, and you know, don't need to worry about all this stuff. So I'll just use rem. And it says you give it 3 registers, RD, RS, RT, and it sets RD to be the value of RS mod RT. So let's try and throw that in our code. I'll say rem, I want to do something mod something, which is input mod 3. And I run into a bit of a problem. Let's just give it a go for now. So we're trying to do input mod 3, but it's expecting a register over here. There's a chance Spim does basically pseudo instruction this thing and let it work for you, but I'll just make this sort of do what we want. I'm going to put the value 3 in a register so I can use that value 3 there. So now what I've written essentially is input mod 3, because we know 3 is going to be in T1 because I just did that. And I need to tell it where to store this result here. I could store it in something like T2, but I could also be a little bit clever and say, I am not going to need to use this T1 value anymore. I just needed it for literally just a second to use this, so I could put it in T1. If you're even cleverer, you could probably notice that we don't even use input again, so we could probably put it in T0. I'll just leave it in T1 in this case. So this line here is saying input mod 3, and we're storing that result in T1. Is it good practice to use tabs, e.g. LIV0? I think Shri has smaller spaces. Yeah, Shri's assembly style could use some improvement in certain places. But what I would strongly suggest, the assignment will say this in big important text right at the very top, set your tab width to 8. There's also a URL in the assignment code that says, here's how to set your tab width to 8 for whatever it is you're using, and then use your tabs to separate certain things out. The reason being, I can just scan through like my first column over here, my brain scans down here, my eyes rather, I guess. And I can see all the labels in my program. I can see all the instructions when I look down this way. I can see all the arguments when I look down this way. And then somewhere off to the end here, it's usually a nice idea to try and align your comments a little bit like this, not particularly the end of the world in all cases, but you can now see comments down that column there as well. So yeah, good ideas. Okay, so I've got that input mod 3. Now we need to check if it's equal to 0 or else if it's not. So first thing to do when we're translating this kind of an if statement, I would suggest is to create the labels for the different sort of sections you need. So in this case, I'm going to suggest we need 3 labels. Specifically, I'm going to start each of these labels with main __ just to make it clear that these labels are inside my main function, because there's no sort of idea of like actual functions in Mips. So we have to do a bit of the work ourselves. So I'm going to say main if true. I'm also going to say main if false. And I'm also going to say main if after, or you could say this is post, or you could say this is end or something like that. I'll just call it after in this case. And what do these labels correspond to? This should be main if true. This should be main if false. And then whatever comes after the if statement, excuse me, should be main if after. So now that we've got these little blocks set up, let's forget about the whole checking the condition for now, do these printfs, and then we'll come back and figure out how to jump between these different labels once we've done the print. Okay, so I've realized that I've made life, oh no, life is okay. So I need to make these strings in my program. I can't unfortunately just type like, you know, print blah, 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 blah in my program just like this. Instead, I have to define a data section. Although all this code here isn't data, this is actually going to be, you know, my actual code. So I need to change back to the text segment before I start that. So now I've got a little spot in my program up here where it says everything in this section here is going to be data for your program. We really in this course only generally use data for storing strings that we're going to use in our code and for storing global variables, of which we don't really have any over here. So I'm going to say, I'll make a string. Since it's inside main, I'll also prefix it with main __. And I'll say string, let's say is divisible like that. And I'm also going to have a string for main is, let's see, is not divisible like that. How do I define strings? .ASCII Z and then my string there. The .ASCII is saying this should be ASCII text. So, you know, throw that there. The Z there is saying that we want the string to be null terminated. If you remember that concept from 1511, each string has a \0 null terminator at the end. That's something we definitely want in our Mips code so it knows when to stop printing. So I'll copy these strings across. Your number is divisible by 3. Like that. My syntax highlighting is dead because of the bang there. Your number is not divisible. Oops, divisible by 3. And then what else did I say after that? Just a big boo exclamation point, new line. Okay. Boo exclamation point, new line. All right. I'm not auto testing, so I don't need to worry about copying the exact strings across. So lucky me. Is there any reason to use .ASCII? Very, very, very rarely. Very rarely. So probably not. Can we write rem T1, T0, 3 directly? Unsure. Spim may support this, Spim may not. You'd have to test it out and let me know because I can't quite remember. But if you do write that, Spim will essentially turn that code literally into this. So it just does a little bit of the work for you. Is it recommended to write data above our text? I notice in the lectures data is underneath the code, or should we alternate between data and text in our program? That's a really great question. So you save yourself a little bit of hassle because when the program if you just sort of like start at the top of the program and start going down, Spim will assume that by default, you start in the text segment over here. So if you don't have any of this stuff, oops, if you don't have any of this stuff here, it'll just assume you're starting in text. So that way you can just write, you know, .data down here and it'll assume this is all text and then you switch to data and do all that. I, for some reason, prefer to put my data up the top and then switch to text. I'm not 100% sure. It's hard to justify exactly why I like doing that, but I tend to. I just prefer seeing the data immediately, but it's either will work. So really good point. Okay, so we were going to print this prompt out over here. We're going to print this prompt out over here. So we need to figure out how to print a string. Back to the documentation, back to my blinded face. Printing values is another set of system services that we have here. Print int, print float, print double, print string. Print the null terminated, right? That's why we use .ASCII Z for the null terminator. Array of bytes referenced by A0 to the console as an ASCII string, right? So if V0 is equal to 4, it says system call 4, then we have the address of a string in A0. It will produce no result, but it will print our string out to the console. So system call 4 is what we're looking for. So I'll say put into V0 the value 4, because syscall 4 is print string. We need to put the address of our string into the A0 register. Luckily, there's a very nice instruction, LA, load address, into A0 of main string. Which string do we want to do? This is if it is true, therefore it should be divisible. And then we should be able to do a syscall. Okay, let's do a similar thing over here, except we want to do not main string is divisible, but main string is not divisible. Syscall. And then afterwards, we should just end up returning 0. Okay. If you're looking at this and saying, I think there's going to be a couple problems here, you may be right. I'll lead us into those. I'm going to make a couple little errors here, and we'll see. We'll try and figure out exactly why that's happening. So we've got our true case. We've got our false case over here, here and here. We know where after the if statement is. Now we need to actually check if this input mod 3 was equal to 0. So how do we check if something is equal to 0? Back to the documentation as per usual. And we should be able to see if we go to our instructions and scroll, we'll get down to the branch and jump instructions. These instructions are our bread and butter for checking conditions. We can see that there's branch on equal, where the values in 2 registers are equal. Branch when it's equal to 0, when a register's value is equal to 0. Branch when one register is greater than another. Less than, there's tons of these. Branch greater than or equal to 0, and link, like, it's insanity how far some of these go. But what are we looking for here? We're looking for if something is equal to 0. So we should be able to say branch on equal to 0 and just give it a register. So let's give it a try. Branch on equal to 0 if T1, because that's what holds our remainder over here, is equal to 0, then where are we going to branch to? Then we'll branch to main if true. Right, if T1 is equal to 0, so if input mod 3 is equal to 0, go to the true case. Perfect. If it's not true, right, if this is not equal to 0, it'll just continue executing the very next instruction. That's sort of what Mips will do. So right here afterwards, I can say, if it's not true, just jump straight to main if false. Right, so what happens now is if input's equal to 0, sorry, not input equals, if input mod 3 is equal to 0, it will go to this true branch. If that's not true, it'll continue on to the next instruction, which just says go straight to the false branch. And now we'll be here printing our string. Again, there is a small error here. So if you're starting it, so let's I haven't written, okay, that's fine. We're going to run the code now, and we'll test out a couple cases. Can anyone see where this code might have a bit of a problem before we start to run it? Since we haven't learned Mips functions yet, can we already start working on the assignment? We've been learning functions in the lectures today, so definitely go through that and have a look again, and have a try at the assignment rather. We did part of, yep, does not ever end after main if true will run on to if false, need the main if after, both will be printed. Okay, we're starting to catch on to this. If we try and run this, bim-f if.s, you'll see it waits for our number. Let's say I give it a number that's not divisible by 3. Let's say 4. It says your number is not divisible by 3, boo. Perfect. If I give it 5, not divisible by 3, boo. Cool. If I give it 6, your number is divisible by 3. We get the behavior we want. And then it also says it's not divisible by 3. Like it can't be both. So, how is that happening there? And as the chat's saying over here, our issue here is that if it was true, right? So 6 was divisible by 3. We'll go into this one. It'll do the print string syscall, but these labels are just like little markers in our program. They're just little markers to say, hey, I'm talking about this bit of code over here. The address of this instruction over here. So what'll happen is, as far as spim's concerned, I'm going to execute this instruction, then this one, and then the next one, which will just be here. And then it'll go this one and this one and this one, and then it'll go to after. So what we actually need is, if it was true, we don't want to also do the false thing. We want to be done with our if statement. And that's why we have our main if after label over here. So I can say jump to main if after. And now, if the true branch goes, it'll print this string and then go, no, don't do the false branch as well. Just go straight to after it. We don't actually need to put it on the false branch here because it just goes next instruction, and then the next instruction will be in after anyway. So we don't end up with that program. With that problem rather. And now we see divisible by 3, boo, boo, and divisible by 3. Cool. Okay. We've used up a chunk of time, so we'll do while loops still. We might run a little bit over time, but we've got 2 hours and the rest will just be study session, I imagine. So do we have any questions about anything this code is doing here? I'll try to scroll to like the main chunk of it, and I'll try and open up most of the C over here as well. Just to field if we have any questions for a little bit, and then we'll move on to, doing some loops next. So any questions? Thank you, Hayes. That's very nice of you. Alrighty, I'm not seeing questions pop up in the chat. As I always say in my tutorials, since we're on the internet, if you're still typing a question and you're looking at me moving on, don't delete your question, keep typing it, hit enter, and we'll bounce back. It's very easy. But for now, we'll start moving on then. And we'll have a look at translating some kind of loop. So of course, I'm gonna have to do ye old faithful, includes standard IO, main, void, blah, blah. Probably return 0 would be nice down here as well. And I guess while we're at it, why don't we set up the basic Mips file, main, liv00 $JR$RA, and say that that's return 0. See, the starter code is even easier in Mips than in C. Could we possibly, after while loops, write a program using the stack? Yeah, we'll do a functions example. Maybe we'll do something recursive or something like that. So we'll have to end up using some of the stack, and then that'll probably take us to the end of the talk, do a Kahoot, and then do the study session stuff. Cool. All right. So there's a couple different loops that we can use in assembly. I'm thinking that since we, in my tutorials this week, I've been covering do while loops since they make a bit of a feature in the assignment code. And specifically because do while loops are really, really simple compared to normal while loops to implement in assembly. You may think that we're really mean and grumpy and we don't know what do while loops are. Why are you including them in the assignment and making life harder for us, for us? That really isn't the case. Do while loops, you will find very soon, are way simpler to implement in assembly. So we've sort of done a little bit of a favor of of including do while loops in the assignment instead. So let's do one of those. I suppose let's do a it'd be nice to read from an array at the same time, but I think we may have to leave array stuff out of this talk, unfortunately. So let's instead just do a little printing exercise, like a countdown or a count up or something like that. So let's do a countdown, let's say. So we start with we'll get input from the user, let's say like 30. Then we'll basically go 30, 29, 28, 27, all the way down to 1 or 0 or something like that. So we'll get some more input, scanf %d into our input over here. And I'm going to do, like I said, I'm going to do this with a do while loop instead of a normal while loop. So a do while loop looks roughly like this, right? Compared to our normal while loop. Our normal while loop looks like this instead, right? So this one we should be very familiar with. This one we might not have seen quite as much of. They're actually really, really similar. A while loop checks the condition and then it runs, if the condition's true, it runs all the code inside here. And then once it gets to the bottom of this brace here, it goes up and checks again. And if it's true, it runs the code in the braces again, gets to here, checks again. Eventually it's false, and then it just goes to afterwards. A do while loop starts sort of running the code and immediately, no matter what, starts executing the code that's inside here, right? So it'll always run at least once. And then once it reaches the very bottom here, it checks this condition. And if this condition is true, it jumps back up for another go. So it'll do the thing, check again, do the thing, check again, do the thing, check again. Eventually, we're assuming that this statement will be false. And once it's false, it just continues onwards. So you can think of it as a do while, you can think of a do while loop as a while loop that always runs at least once per se. It just checks the condition at the bottom. So let's try and make this work. Do while over here. So we are going to count down. So we're probably going to say inside this loop, we'll print their number. So let's go print input. I'm just going to overwrite. I'll just subtract the value of input just to make life a little bit easier as we go. So let's say we printf the input. We'll subtract 1 from the input. So input minus minus each time. And then what do we want to check? We can check while input is, let's say, greater than 0. You have to be a little bit careful with your bounds checking. Let's say greater than or equal to 0. So we get 0, 1 as well. But if we think about this, if they input, say, 10 or whatever, we'll get 10. It'll print 10. Then we get 9. 9 is greater than or equal to 0. We'll get 9 again. Then we'll get the 9 printed out, make it 8. Then print 8, make it 7. Print 7, make it 6. Eventually, all the way down, we'll get to input minus minus becomes 0. 0 is greater than or equal to 0. So we'll print the 0 out, subtract 1 from the 0. We'll get -1. Then we'll fail the while condition and the program should go on to exit. Maybe we'll add a little bit afterwards here that goes like boom, if it's like or maybe let's say lift off, if it's like a countdown for a rocket or something like that. Okay, so let's test out this program again, just to make sure it's doing what we want. Loop C loop. And I need to give it a number, let's say 10. And it says 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, lift off. Cool. What's the final exam format like? The final exam will be a mixture of theory and practical questions. I can't really say much more than that, sorry. So now we get to translate into Mips. So let's do the stuff that we're already vaguely familiar with, which should be getting some input, which if you remember is syscall 5. So syscall 5 is read an integer, run the syscall, and then let's put that value that we read in, which will be in V0, into instead, let's say T0 register. Okay, cool. So now we should have input in our T0 register here, and we're ready to do our do while loop now. Here's just how easy doing a do while loop can be. So we need to think about, it's okay to throw in a bunch of labels at first to help you sort of structure everything and then delete the labels after if you find you don't need them. So I'm going to say main __ do, which refers to the beginning of this do over here. Let's say we have main __ condition, right, where it checks the while loop condition. And let's say main after, where it finishes, it's after the while loop, which should be this lift off over here. Turns out we're actually not going to need some of these labels. Preference / reasons for using $T and $S. By default, reach for a T register. We'll see when we need an S register in probably the next example. I'll talk a little bit more about that. Okay, cool. So we've got our do block. Let's start writing this code here. So we need to print an integer, print our input integer, print a new line, and then do input minus minus. So let's try that code out. Go back to our documentation. Printing values. Print an int is syscall 1, and our integer that we want to print goes in A0. So syscall 1 is print int. Then we need to put the integer we want to print in A0. So into A0, I'll put the value in T0 because that's our input. And then I'll say syscall. So this is equivalent to saying, printf %d our input. Finally, we want to print the new line after as well. So If we want to print a single character out, that would be syscall11, and the character goes in A0. So syscall11 is print character. I can load a character as an immediate value as well into A0, a new line character. This essentially uses the ASCII value of the new line character for us, and then do a syscall. And this is essentially the same as saying printf new line. Oops. So we have this whole printf done there. And next we just have to do input minus minus. You can sort of do this in a couple different ways. The one that I tend to use is a add immediate value, right? I actually tend to use the add immediate value unsigned. It should say unchecked is a better way of saying that. Another badly named instruction. But just to keep things simple, I'll use add I in this case. And we say add I takes a register and immediate value. So in this case, we'll give it T0 being our input, and an immediate value, I'll say -1, and it'll add those together and store it into the first register here, which I just want to be our input again. So what this line says is input, being in T0, equals input plus -1. So subtract 1 from the input and then set that to be our new input's value. So that should be these 3 lines here. I'll add a little comment saying that this is input minus minus. And that's our do block. Now we need to do the while. So this comes at the condition here. And the condition needs to check while the input is greater than or equal to 0. If we go back up to our branching instructions that we were looking at earlier, branch and jump, I believe we should have BGEZ, branch on greater than or equal to 0. So we give it a register. It says if it's greater than or equal to 0, then go to that label, branch to that label. So we want to branch on greater than or equal to 0, where T0 being our input is greater than or equal to 0. If that's the case, we need to jump back up to the beginning of the do block here, being main __ do. Now, here's where things start to become a bit apparent. What happens if this branch greater than or equal to 0 doesn't branch, right? If it's not true and it doesn't branch up to the main do block, it'll just go on to the next instruction, which just so happens to be after the while loop, right? There's none of this if trickery where we have to jump from one label to another so we don't accidentally do the other thing and blah, blah. You end up with the same thing or a similar sort of thing in a normal while loop, whereas a do while loop, you just branch. If the branch fails, you go after. So this label isn't needed at all because it'll just move on to the next instruction. And this label isn't needed at all because at the end of the do block just comes the while condition. So this is actually literally all you need. I could write this as like while input is greater than or equal to 0. And maybe I could even add a comment in at the beginning of this here saying do at this block. And that is quite literally all the code. Like, this is why I say do while loops. Well, okay, fine. I haven't printed lift off. I should probably do that. But do while loops are literally, I was about to use that exact terminology. Do while loops are literally OP. Like, so little code, so little thinking, just do this stuff and then check the condition and maybe jump back up again. So I'll do the print lift off. So as per usual, we need to do a string. I'll do it down the bottom here this time just to show it coming in different ways. Lift off, I'll prefix it with main as well. Main lift off is a .ASCII Z of the string lift off, bang new line. Cool. And to print a string, what was our system call there? It was print string system call 4 with the string's address in A0. So, oops, system call 4. Syscall 4 is print string. The address of our string goes in A0. So load address of main liftoff, and then syscall to execute that system call. So this is printf lift off, bang, new line, like that. And this is our final code there. Why do you use double underscore in label names? You could use a single underscore. You could, make it sort of whatever you want. You could, I'm trying to think of what other characters and labels Spim is happy with. You might throw a bunch of zeros between. I just do double underscore to make it clear that this is like inside main is this do label. For main, or like inside main is this lift-off string here. So it just sort of helps you out. Why is the last new line gray? That's my syntax highlighter being very upset about an exclamation point. It's just not the best, clearly. So let's give it a try. There very well may be some bugs in here, so we'll find out. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, liftoff. Let's try it with 100. Cool. 100 all the way down to 0 and then liftoff. So that then, I'm at least relatively convinced, should be our final code. So again, I'll stop to see if we have any questions about the loop translation, how the sort of Mips is looping together. If we need to, then I can do a bit of drawing or something like that to help make things a bit clearer. We want to try -1. I assume it's probably just going to say liftoff. Oh, it says, because it's a do while loop. Right. As we said, it will always execute at least the first time before it checks the condition. So it will print the first -1, no matter what. And then it goes, all right, I'm done with this loop. So a great example of, me not even realizing that that was going to happen before I did it. Do while loops can be a little tricky. So you need to be pretty sure that when you're using it in the right way. It's doing what you want it to do. I can combat this edge case by just saying, that's what I want it to do. Therefore, the do while loop is correct. But that's a really great point, really good test case, as Kaki pointed out. Cool. Any other questions about this code? Any other clarifications? Blah, blah, blah. I should probably move my Subway cookie out of the way so I have access to my drawing tablet if we need to do a bit of drawing. We probably will for the next example. So let me move that around a little bit. Cool. Not a bug, it's a feature. Exactly. Perfect. Awesome. Cool. So what have we covered so far? I had to drop out. We've just covered translating an if statement. Now we've just done translating a do while loop. And now we're about to do translating some function calls. In this case, let's do a little recursive function. I think factorial should be good. If there's a specific, function that you were hoping was going to make an appearance, let me know. It's not too late to change it around again. But for now, I'm just going to continue on with factorial. Cool. So how does factorial work, in case you haven't heard of it before? If I say, what is the factorial of, let's say, 7? It's essentially equal to 7 times 6 times 5 times 4 times 3 times 2 times 1. Like that. So you just multiply all the numbers that are like it and less than it. In fact, now is probably a good time to open up a Paint application, because I want to just demonstrate a quick property of factorial, which makes it quite interesting for us that not all of us may be familiar with. Okay, cool. It seems to be working. The interesting thing about factorial, which I'll just write as fac of n, like that, is you can write it like this. So we know that it's essentially n multiplied by n minus 1 multiplied by n minus 2, ... all the way until we get to like 3. That's a really bad 3, 2, 1, like that. But there's a really neat way that we can write this factorial function recursively. Recursively is a term that refers to a function using itself in its own definition. So we'll see in a second. We can write factorial as this. Let's just say if n, I'm going to probably upset some of the math purists out here. So just, whatever, I don't care, bear with me. Let's say if n is greater than 1, I understand this is not mathematically, whatever. It will be n multiplied by the factorial of n minus 1. And then otherwise, if n is not equal to 1, is not greater than 1 rather, you just get the value 1. Okay, why does this make sense at all? Well, let's say if we plug in the example factorial of 3, then we follow this definition. 3 is greater than 1. So what we get is 3 multiplied by the factorial of 2. Okay, so what's the factorial of 2? That's following this definition here, to be clear. 2 is greater than 1. So we get 2 times the factorial of 1. So we get 3 times 2 times the factorial of 1. And then 1 is not greater than 1. So we just get the value 1 here. It just says else it's the value 1. So in total, we just get 3 times 2 times 1, which is our correct answer over here. So this is a really, really neat way to define our factorial function. If n is greater than 1, return n times factorial of n minus 1, otherwise 1. Okay. If we have questions about this, please speak up because it can be a bit tricky and I can do a bit of a crappy job of explaining things very often. So let me know if we need to sort of run through things a bit again. What may help is seeing exactly how we implement this in C, which ends up being quite easy. If we follow this definition, if n is greater than 1, as we said, then we simply return, so give back the value, n times the factorial of n minus 1. Return n multiplied by the factorial of n minus 1. Otherwise, let's say else, we just return the value 1. Oops. Now, you may be surprised to hear that that is it. That's all you need to do in C to make the factorial function, and it works. So let's just make a couple quick test cases. Oh, let's not do test cases. Let's do a scanf and stuff. Input scanf %d into our input variable. And then we'll say, let's say int f equals the factorial of our input. And then finally, we'll go printf %d new line, the f, like our factorial there. Okay, it's complaining because printf and scanf are not defined. So I need to hash include standard.io.h. And now it's happy with me. All right. So this is all the code for it here. Let's give it a go, factorial.c, and run that. If I give it, say, 3, then we get 6, because 3 times 2 is 6, times 1 is still 6. If we do it by force, then you sort of get the same value, but times an extra 4, so you get 24. And we can continue this on for a while, until we probably end up overflowing at about like, I'm guessing around 20 or so. We start overflowing our number. I probably actually need to go quite as far as 20. And you see it's gotten too big to store in a single integer, and we wrap around and get negative numbers. How about negative numbers? Aren't they invalid? Let's say out of scope. I think if you're a real maths nut, you can do, what's it called again? The gamma function and stuff. We're not going to do that in our little simple Mips program. Just let's assume that all the input is positive. Cool. So how do we go about starting to translate this into C? Because now the story's gotten a little more complicated. We don't just have main in the picture now. We also have our factorial function in the picture. So let's make a very simple example here, JRRA in our main, and we'll just JRRA in our factorial. So now we've got like a very basic setup of our two functions, but we need to get them to talk. So before we get onto the specific challenges, let's just get our input and make that happen. V0, 5, because syscall 5 is read an integer, syscall, move into a temporary register T0, being that. So scanf %d ref input. Okay, so I've just read a value in just like the previous two examples into T0. Now we need to call factorial. So this should be our int f equals factorial of input. We don't really know how to do that yet. So we'll just leave that commented. And then we're going to print an integer out. Syscall 1 is printint as per the previous example. And what integer are we going to use? Well, we're going to need to put something into A0, which we'll try in a second, and then syscall it. This should probably be like, f, the value that we got here. And then this syscall will end up going printf %d rather of f. Need to print the new line as well. You can see this is, assembly can be a little bit tedious, but we're getting there. A0 new line, and then syscall, which will be printf new line, and liv00 for our final return 0 here. Okay, there's all of our boilerplate out of the way now. We've got our new line, we've got the printint, but we don't know where our f value is. We don't know how to call factorial, and we haven't written factorial yet. So we've got a bit of work to go. And then we'll be finished off with the talk. Okay, so how do we write our factorial? Let's just write it sort of the way our brain tells us to, and we'll see if we run into any issues as we go. So the first thing to check is if n is greater than 1, but we don't know where exactly is n. Some of us might say, oh, well, n is in T0, right? We scanned that in. That input is going to be used over here, so it must be in T0. But then, what if someone wanted to call our function again? What if they were doing 2 factorials, one after the other, and it just so happened that the number in one of them was in T0 and the number in the other one was T1, right? We can't, our factorial can't just make assumptions that, oh, it'll probably be in the T6 register because that's where I've used it. If we want our function to be sort of generic so other people can use it, or even we can use it multiple times flexibly, we can't be coordinating different registers between our functions, just going, I know it's in T0, so I'm just going to use T0 here. So how do we all agree on how our functions should be called, where things should go, how we should do things? It is something I affectionately refer to in my tutorials as the Pirates Code of Mips. The official name is the Mips calling conventions, Mips standard calling conventions. But it's essentially just a list of rules that everyone tries to follow. There is no real law or anything stopping you from breaking the rules, but to all work together, we all need to follow the rules, and that's why it's sort of important. So that's sort of why I refer it to the Pirates Code of Mips, because everyone always goes, I don't need to do this though. I could break this. I could just go and do that. I'm like, yes, you could, but we're all trying to work together here. We're trying to write good code that we can all rely on. So we all need to follow the Pirates Code, right? So there's quite a few things in the Pirates Code, or the calling conventions of Mips. And here's a few of them to name a couple, I suppose. Arguments for a function, right? So that would be this int n that the factorial asks for, should go in the $A registers. So the first argument should go in $A0, then second in $A1, $A2, $A3. If your function has more than 4 arguments, first of all, probably, do you really need a function with more than 4 arguments? But sometimes you do. In which case we start passing them on the stack in memory, and it gets a bit more complicated. We don't really see that in 1521. But yeah, so we can just assume that our functions will have less than 4 or less arguments. In this case, we just have 1, which means n should be passed in on the A0 register. Part of the Pirates Code also says that our return values should go in the $V registers. Specifically, if you're just returning a 32-bit value, it should go just in V0, because the V0, each register is 32 bits. If you're returning a 64-bit variable, like a long or a double or something like that, then you split half the bits in V0 and half the bits in V1. Cool. So we are going to accept n in on our A0 register, and we're going to give our return value back on the V0 register. There's also certain Pirates Codes rules around T registers and S registers. So here are those rules as well. As far as T registers go, you can do whatever you want with them. You can blow them all up, set them all to be the value 1000, make them all 42. You can set them all to 0. You can do whatever your heart desires to your T registers, and any function is allowed to do that. All these functions follow the same rules. So you're all allowed to just destroy T registers as you please. That sounds all fun and good, but it makes a very important implication for us. If we have our T0 over here, right? Here's our input over here, and I store it in a T register, and then I call a function, I must make the assumption that factorial, this factorial function here, has obliterated every single T register because it's allowed to, right? The Pirates Code says that you're allowed to do whatever you want to your T registers. So I cannot just assume that I still have that same value in my T register after I've called the factorial function. It's an unfortunate sort of circumstance. You must assume that all the T registers have been obliterated. Again, I know, oh, but factorial doesn't actually mangle the T register, or we would call this clobber. The factorial function doesn't clobber the T register. I can see it right there. You still can't rely on it. Someone else may change the code later. It's not following the pirate's code. And in terms of assembly style and stuff, you would, lose marks in the course per se and stuff like that. So you need to follow these kinds of conventions and assume that all the T registers are dead. Now, what if I changed my code here to look a little bit like this instead? If I said %d factorial equals this, right? Let's say I'm changing my code to look something like this. %d factorial equals %d. Notice I have a value in my input. I call a function, and then I need that value in the input again, right? And by the way, the exclamation point is just a shorthand way of saying factorial. If we run this C code, we'll see that it still works. 5 factorial equals 120, and we'll update our example. Like I said, we can change things halfway through, and it's quite fitting for us because now we run into this problem where I have this value in a T register. I call a function, but it's probably obliterated it. So now I can't print it out after I call the function. So how do we solve this issue? And this is where we get onto another pirate's code of Mips, being specifically, you are not allowed to obliterate any S registers at all. You are not allowed to. So factorial, when I like, if I have, 0 in S0 and 1 in S1 and 2 in S2 and 3 in S3 and so on and so forth, like I've set up those registers like that, and I call my factorial function. Once it's finished, those S registers should all have exactly the same values as before. Do whatever you want to your T registers. Don't you dare touch an S register like that. That's sort of the main pirates codes rules of Mips that we have to care about. Now, let's say so that sort of solves our problem. Input, cool. Instead of putting in a T register, I'll put it in an S register. So I know that it'll still have the same value after I call factorial and print it out. That's good. But if you're really switched on and aware right now, you may be noticing something interesting. Main has just broken the pirate's code. And we don't break the pirate's code over here. Main has broken the pirate's code. How? It overwrote the value of an S register. But main's special. Main's the best function. It's the big one. No, it doesn't matter. It has to follow the rules. And we've just broken the rules. We can't overwrite the S registers. So then you go, well, Zach, like the S registers are useless. If I can't write into any of them, like if I can't change the values of any of them, I might as well not even have them. Right. I mean, that's true. Good point. However, there's a trick we can pull. The rules, the pirate's code. This is like we have the book of the pirate's code and everyone's gathered around the table because the pirate's code has a little like error in the way it's written, and we can exploit this error to do what we want. That's sort of exactly what's going on here. The rule says that if I have my S registers as some value, I call a function and then it returns back to me like, we're down here. Those S registers should all look the exact same as before. Now, if we're really clever, we can basically pull the wool over main's eyes, do some trickery, and then undo it all right before we finish. And this is how. So this is how main is going to sort of save that S registers value and make it look like whoever called main to whoever called main, the S register was never changed. The answer is we'll store the S register in memory, right? We'll store the original value in memory at the beginning of main. Then we can modify it and do whatever the hell we want to it inside main. And right before we return, we'll put that old original value back into it. So it looks like nothing happened at all. And that we haven't broken the pirate's code. Everyone's happy, everything works. And that is the exact mechanism by which you should be using S registers like this. Just to really make this point clear and to hammer it home a little bit, let me pull out the old pen over here and make this point very clear here. When we have some function, in this case, usually the function that calls main is actually called _start, run C, blah, 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 whatever. _start will call your function main. And let's say _start just so decides to store the value inside S0 will be equal to 42. Now it calls main, and the first thing main does is it says, take that value inside S0, and I want to save that to memory over here. So we have our big grid of RAM over here, which I'm sure you're sort of familiar with this diagram from the lectures and stuff. My head is, of course, as always, in the way. So hopefully that's a little bit better. And let's just say in memory somewhere, I'm going to store the value 42 into it. The place I'm actually going to store this is on the stack using something called the stack pointer register, but we'll talk about the exact specifics of that in a second. So I save the value of S0 into memory when main starts. I change the value. So I say S0 is now going to be equal to our input, completely destroy the value, do whatever I want with it. And then right before I return, so let's say my JRA, my return is down the bottom here somewhere. Right before then, I'm going to read that value 42 back and set S0 to be equal to that value 42. So as far as underscore start is concerned, it goes and calls main returns back, and S0 will still have its original value 42 back in it. So this is how we can use this little trick to use our S registers and stuff like that. Is there any questions so far about how this little mechanism, this little trick works, apart from like, how do we actually do the saving? Because that's what I'll talk about just in a second now. So I'll let people keep typing their questions. Sorry, I know we're going over time, but we're on a roll here. This seems relatively important. So we'll just keep going, and then hopefully it's not too crazy. Why don't we just have Factorial function access the data in memory directly? Why don't we have Factorial access the data in memory directly? So are you saying, so this is a sort of interesting question here. I'm not 100% sure I'm going to nail the exact point that you're trying to make here. But I'm guessing you're saying, because we're talking about the S register to be using in main here for our input, I'm guessing you're saying, doesn't Factorial just access its argument from memory instead of in the argument register? Or is the question slightly different? Sorry if I'm misinterpreting. So let me make sure I get the question down first before I answer the wrong thing. Compared to onloading data into S0 and then offloading sneakily. So the reason we do that is actually in main, because we have to make the assumption that Factorial is going to destroy all our T registers. So we're not allowed to store our value inside a T register. Although again, Factorial, sorry, my head's in the way of the Factorial function, but you can imagine it's down here. Now we know that Factorial may not actually destroy all the values of our T registers, but to follow the Pirate's code, to make our code robust, we need to make certain that we're not assuming things like that, because it could change in future. And in that case, we need to then use a saved register, and essentially this sort of saving it to memory using the saved register and then loading it back before we return is sort of upholding our end of the agreement. There's a big, agreement, the Mips Pirates code, the Mips standard calling conventions that says, as a function, you must not overwrite the value in an S register as far as anyone else is concerned. So we have to, uphold our end of that. That's sort of what's going on here. Cool. Thank you for the bump. Can we cover frames, users, clobbers, locals, functions? Yes, it is from the assignments comment. I'll try and talk briefly about it, but I won't be able to spend too long on it, I imagine. I'll give us like a 2-minute cover view once we've got our code going, I'll say. Okay. So is Sri breaking the unsaid rules of Mips when he used $SN arbitrarily? Yes. Not the best sort of thing to demo in a lecture, but we all sort of make little mistakes like that. So yeah, you should only be using S registers when you specifically need to, because to uphold your end of the deal, you have to now go do this whole storing to memory and loading back, whole thing like that. So a very good point. All right. So how do we actually store these things to memory then? What's the exact mechanism for loading and storing that in? Sri is not a good pirate. So the idea here is we have a special thing called the stack pointer. Whether you want your stack to grow upwards or downwards, yeah, whatever. Let's say it grows downwards. So we have up here our things like our text segment at the bottom of memory, and then we have this data segment that we know. The data segment can also grow. So the text segment is usually at address 0x004, 1, 2, 3, 4. I think I made another 0 over here. Something like that is where the text segment usually starts. So there's a bit of other stuff down here as well. The data segment, I believe, usually starts at, I don't know, it's something like this. It's been a bit long since I remember. And the data segment can also grow dynamically. It can increase in space. It might start off at this space here when you when you run your program, but you can expand it to say be like this big as you keep going. We also have the stack, which lives right near the end of our memory over here. And the stack can also grow, but it grows in the opposite direction. In practice, the stack and the data can never really clash. Like there's so much distance between them. You know, my diagram's not to scale, that they never really crash and the stack can't really get that big. But the stack usually starts way up here at like 7F, F, 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 you know, roughly 8, and then a bunch of zeros at that point. And the stack grows sort of downwards in a certain sense. So we have this special register $SP that we haven't talked too much about up until this point. And the idea is $SP points at the very top of our stack over here. Why is this particularly useful? If we want to store something in memory and then restore it later, we can do this little trick. Subtract from the stack pointer how many bytes that we need. So for a register, each register is 32 bits, being 4 bytes. So we'll subtract 4 bytes from our stack pointer. So now it'll point, say, down here. And what we say by conventions, by the Mips Pirates code or whatever, this here is our memory to use. And that's where I'm going to store my value for $S0 in here. So I subtract 4 from my stack pointer. And by the sort of Pirates code, I say, this area right here is my 4 bytes for the keeping. Other functions might go and allocate more, as we sort of call them. They might allocate this, blah, blah, blah. But as they finish, they'll clean up their own resources. And sort of like how you free your mallocs, they'll free up their stacks that they use, you know, their stack frame usages. And then eventually when they get back to us, the stack pointer should be right where we left it as well. And we'll be able to go grab this S0 back off the stack. Okay. So this is all a bit crazy right now, but once we see it in practice and you see a pattern to follow, it's actually quite easy to use. So we have to subtract 4 from our stack to allocate ourselves 4 bytes. So I'll say add immediate. I'm also going to add the U there for unsigned, what should really mean unchecked, which just means that if there's some sort of integer overflow, it won't crash my program. That's all it's saying. Sorry, not S0. Subtract 4 from our SP. SP minus 4 and store that inside SP. And then I say at the stack pointer, I want to store my S0 register. So I'm going to write it like this. Subtract 4 from the stack pointer. And then at that, you know, at that, the spot that I just allocated on the stack there, store a word being 4 bytes because our register is 4 bytes, the value of the S register at that point. Now, that will save it to memory. That does that like arrow that went across my thing over there to save it to memory. I also need to restore the original value from memory before I return. So I'm going to basically copy this code, reverse the order over here. So instead of storing it now, I'm going to load it back from, again, that same spot on the stack and then into S0, right? So that'll take the value again and store it back. Let me move my head back across now at this point. And then I will sort of free my stack usage. It's not the same as free, but I'm going to add 4 back so that the stack pointer is now pointing back here again. And this stuff here is all freed over there. So we're not using that anymore. That's all there is to saving and loading things to the stack. Super handy. And now I've followed my side of the rule and I can use this S0 register in main and no one will be able to tell that I've modified it at all. Why are there brackets? Great question. Sorry, I forgot to cover that. The brackets here are basically just saying that this register has an address. It's a bit of a like Mips syntax thing, not really for much reason, specifically because you can say, you can imagine there's a little 0 here that says, I want to store it at the stack pointer, like the address of the stack pointer plus 0. And you're able to put like any number here, like 4, 8, 12, 16. And this will do like stack pointer plus 16. Since I'm just storing it straight at the stack pointer, I don't need to put any number there, which will sort of implicitly put a 0 there saying stack pointer plus 0. That's why it sort of has those zeros. Can you do negative? Yes, you can also do that. -4, -8, so on and so forth. Cool. If I'm not touching, for example, $S8 throughout the whole code, do I still need to store it in the stack by convention? If you you only need to store an S register to the stack and restore it afterwards if you modify it in your function. If you're not modifying it anywhere, then you don't need to store that S register. If you do modify it, but you're not really planning on using that register anywhere else, you still need to store it. Yeah, even if you're not planning on using that S register anywhere else, to uphold your end of the pirate's code, you need to store that S register to memory still. If you don't clean your stack, is it like a memory leak? If you don't clean your stack, it's much worse than a memory leak, because some function that might call main will often assume that the stack will now be pointing at my data over here. But instead, it may be pointing at your data over here, and it gets the wrong stuff, and then everyone's confused, and the whole program starts doing really weird things. So always remember to clean up your stack at the end, lest you may suffer, bad consequences. SP is the number of an address, and that allows you to access sort of like its memory. Yeah, cool. Using our load and store instructions, that is. Okay. So now we've stored the S register. Let me write a little bit of code for this. I'm going to make a quick string over here. Data, we'll call it main __ fac eq, like that. Will be dot ASCII Z of Vohio. Cool. That's not what I want it to be. Thank you, Twitch, for keeping that for me. Bang space equals space, like that. So that'll just be the string that goes between these two things. So let me sort of get our code for that as well. V01, because syscall 1 is print an integer. We want to print out our input, which was in S0 now. So that's going to go into A0 and syscall. That's going to be, not syscall, printf %d input. I need to print that string. V04, I think, is print a string. Syscall 4 print string. And then we want to load the address into A0 of main __ factorial equal syscall. So this is just going to be our line, exclamation point equals space, like that. And then we print F and then our new line like that. Okay. So just a little bit of extra code, feel free to look at this again in your own time after the thing. But it's, not too crazy there. Okay. There's one more issue we have to talk through. And then we will basically be ready to go to finish off everything here. Sorry, I understand this has gone on way longer than we're expecting, because it turns out functions can be a little bit tricky, but hopefully this helps. Okay, so the one other thing that's a bit tricky here that we have to think about is, without considering factorial calling itself for now, just main calling factorial, we need to think about what happens with its return address, because we're going to get quite a weird issue. Let's in fact leave factorial as it is now, or let's say factorial just always returns the value, 5, sure. So right now factorial just says return 5. And as we said in the Mips Pirates code, return values go in the V0 register. So we're ready to call factorial, and we'll see what happens here. So to call a function, we use JAL, jump and link. So I say jump and link to factorial over here. What that'll do is it'll jump to the label like a normal J instruction over here. And it'll also do a link, which says set the return address register to be the address of our next instruction over here. So that'll be this one, which basically says when factorial returns, when it does JRRA, make sure you go here right after where I called the function, like it would in C. When we say in C, call it, it should just move on to whatever the next thing is after it returns. So that's what jump and link does. Factorial also expects the argument. It's not using it right now, but it expects our input argument to be in the first argument register, A0. So we'll set that up as well. Into A0, we'll put the value of S0, and then it'll put our return value, the actual factorial, into the V0 register. Let's put that in, say, T1. And you'll notice I can put it in a temporary register because we're not going to call any more functions. So there's nothing to wipe my T registers out after this point, which now means my question marks over here, when we're trying to print out the F, the return value here, that's now just going to be simply $T1. Oops. Okay. So line 3 should be, oh, thank you. I don't know how to spell ASCII clearly. Great point. Okay. So that should be most of our program there. Main is pretty much done at this point, but factorial just returns 5. There is an important bug though. This may be unexpected for some of us. Some of us may see this coming if we've done some function stuff before, right? And particularly Raman here seems to have a grip on what's going on there. Ooh, we've got this really big, nasty error. This is stack. This is what happens when you have a bad stack as well. Since we have this, essentially what's happening is we have an infinite loop, but because of this stack frame stuff, it's turning this infinite loop into a incredibly large, crazy error, which is, what I said can happen if you're not careful with your stack frames. But let me try and walk through exactly the sort of what's going on here. Now, like I said, there's a function that calls main. That function usually called something like _start. _start will do a JAL, jump and link, to main. So it'll jump to the main address, like the address of, main's first instruction. And it will also set the return address register to have where main should return back to. Here's our problem. Main continues on and then says jump and link to factorial. So it says, great, I'm going to jump to factorial and link. I'm going to set the return address value to now be this instruction, whatever is right after our jump and link. So factorial knows where to return to. But because we were so worried about making sure factorial knows where to jump back to, we just completely forgot about where we need to jump back to, right? We overwrote the value in the RA register, and now we don't know where to go back to. So when this code continues, it'll do its thing, but this JRA won't return back to _start or where spim called our main from. It'll return back to here because we forgot where we need to go and just got stuck, going back to where we told factorial to go, because that's just what the RA register has now. So to solve this issue, no mistakes, happy accidents, absolutely. To solve this issue, all we need to do is also save our return address to memory here, restore it from memory before we return back. So basically we're saying, don't forget what our return address value is here. So I can basically just repeat this sequence, by the way, allocate 4 bytes in the stack, store a register, allocate 4, store a register. In this case, I just want to return, store the return address. And then we have to make sure that we do this in the opposite order once we're pulling it off. So the last thing that we threw onto the stack was S0. So that needs to come off first. If we're storing it like, here's the return address, here's the S0, then our functions might go off and do some other stuff. It comes back. We need to pop off S0 and then pop off our return address in that order. So in fact, I can copy paste a bit again. Oops, not that one, like that. And I'm going to load in the return address register first. So then when I do this JRRA, it's using the original value that I saved to memory first. Will it fail to load if we do it in an arbitrary order? If I did this in the other order, it will put what was S0's value into RA and what was RA's value into S0. It'll put the wrong value in the wrong register. Specifically because if you think about the stack pointer as like a pointer moving up and down, we said return address goes here, move down, or sorry, rather like move down, return address goes there, move down, S0 goes there. So when we're pulling it off, we need to say grab S0, move it up, grab RA, move it up. Sort of like that. Yeah, I don't know exactly how I'm going to do that, but I'll make sure these files are available for us to use afterwards. Cool. And if we save this and run it, oh my God, we still have a crazy stack exception because I've clearly messed something up. Did them in the right order there? JRRA. That's interesting. Oh, okay. That's definitely still going off. Does anyone spot the error here? Because I don't immediately, and we're going to have to do a little bit of debugging if someone hasn't noticed my mistake. Is add IU, add unsigned immediate? Yes, but that unsigned should really be the word unchecked. Just means that it doesn't fail if there's integer overflow. Load word, RASP. Ooh. It's really worrying when I'm looking at all this and it all looks relatively good to me. Okay, that's pretty fun. Other way round, RA then S0, S0 then RA. No, I think it should be like this. I mean, I can swap them around. Oops. And we'll see, yeah, that still happens there, unfortunately, because we need to do it in reverse. A stack is what we would call last in, first out. All right, so we have a little bit of debugging to do. So now we get a quick lesson on how to do that. Target of jump differs. Oh, wait, what? No, that can't be right. How did it get that idea? I do know what it's saying here, but it shouldn't be saying that. My spim is having a freak out. Factorial.s. Okay, we have, okay, you know what I'm going to do? This will be quite entertaining if this ends up working. I'm going to copy factorial.s onto CSE, USLEDU, like that. Oops, that's not going to work. And if this ends up working, that'd be really funny. Let's give it a quick go. It may be my spim is broken because my spim is like doing some weird things. Spim-f, sorry, 1521 spim-f factorial.s. No, we get that same thing again. Ooh, oh, I know what this is. I know what it is. I think this is a great one. Wow, spim, that's not a good error message, my guy. .text. Wow, what a terrible error message. Wow, isn't that great? That is just real hands up to
what would have happened if we ran that with Mipsy?
What would happen if we ran that with Mipsy? I don't know. Do I have, what is Mipsy an alias for? That might work. Factorial.s. It says not yet. Yeah, so it hasn't implemented that idea yet of instructions going in data segments. So interesting question. I haven't gotten around to that clearly, but you know what? I'd rather Mipsy crash than do that. That's wild. Okay. Now that we've gotten past that very great issue. So actually, this is worth committing to memory. If you see this error here, target of jump diff is in high order 4 bits, good chances are you've forgotten to put .text before your code. That is brutal. What a good one for a live talk as well. Okay. All right. 5 factorial is 5, right? Because it always returns the value 5 because we haven't written factorial yet, but it looks like it's doing what it should now. What a complete nightmare. Just to also show us really quickly what would have happened if we didn't save our return address to memory. So I've just removed the stack stuff doing that. There's the infinite loop that actually comes from not saving the return address rather than forgetting .text. Wow. Okay, cool. That was a great one. That's not what I want to see. Okay, cool. So this is all doing what we want. We just need to implement factorial now and we're done. Well, then we'll run our Kahoot, of course, as well. All right, don't need CSE anymore. Okay, so factorial, this one shouldn't be too crazy to do. There is one important thing we have to keep in mind here, which is that factorial does call a function inside it. It calls the factorial function inside it. Therefore, it needs to do the same thing as main. It'll end up forgetting the correct return address because it calls another function and loses that RA. So you're absolutely right. We must save RA in factorial as well. So I can just, steal my own code here a little bit. So that should save the return address. This should, oops, that's not what I wanted to do. That should restore the return address. Cool. And now we're ready to go. So that should save our return address and we do our little checks. So if it's greater than 1, if n is greater than 1, we can probably do a branch greater than BGT. You'll find it on the spin page. N is going to be in the A0 register because it's our argument. And when you say if n is greater than 1, I know it expects a register here. Spin will sort of let us do this and translate it for us. I can just say if n is greater than 1 here, then we'll go to factorial true. So let me do that. Factorial true, factorial, let's do false as well, and factorial after. Something like that. So if it's not true, then we need to go straight to factorial false. Now, what is factorial true going to do? Factorial true needs to do n multiplied by factorial of n minus 1. And we run into another really annoying thing here, unfortunately. It won't be too hard to fix because we've already done this once before. But the problem here is if I call factorial of n minus 1, how am I meant to take that value and then multiply it by n if, factorial can wipe all my registers? And, we're going to have to set up the A0 register to pass this argument. I'll show you what I mean. We'll do an add immediate of our, we take A0 and subtract 1 from it to make this n minus 1. And we need to store that in our A0 register as well to call factorial again. Right? This is factorial setting the argument to be n minus 1 for factorial, which because the argument needs to go in the A0 register here. So now we've actually lost our value of n because first of all, we've overwritten it like this to set up a factorial. And as far as we know, factorial is just going to wipe all this stuff. However, we know factorial isn't allowed to wipe S registers. So we're going to add another S register in here. We'll save the value of S0. I probably should do this in the opposite order. So I'm going to do that. Usually I like my return address to be on the very bottom of the stack, like the very first thing that we push and the very last thing that we pop back off at the end. So now that that's not how you restore a register, of course. Let's put that here and then delete this away. That's not what I meant to do. Actually, yes, it is. This just needs to be S0. Sorry for the confusion for a bit there. But now essentially we're storing RA, we're storing an S register, we're loading the S register, we're loading the RA back. So now we're free to use S register, like S0 rather, as we please during our function. So the very first thing I'm actually going to do is just to make 100% sure, straight away, I'm going to throw into S0 the value of n. Now we'll always have the value of n inside our factorial function to use inside that S register. So I'll make this use S0 as well. I'll make this use S0 minus 1 to give the argument to the next call of factorial. And once we've done this factorial of n minus 1 here, we should just have to multiply that value by n and return it. Where are we going to return that value? Into the V0 register. So I should just be able to say multiply where this factorial returned its value, which would also be in V0. Multiply that by n, which we know is in S0. And that's going to be our return value. So our return value also being in V0. So this sort of 3 lines right here is saying n times factorial of n minus 1. And since I'm putting the final result here in the V0 register, that's what our factorial will end up returning. And we have to make sure as well to jump straight to factorial after as well, so we don't end up with the same bug as in the first example. We don't want true to then run the false code here. What's the false code? Really easy. It's just going to set the V0 register to be 1 because it's just returning the value 1 no matter what. So this here is just saying 1, essentially. And finally down here, it's really saying like return the value that we sort of did in those if branches up there. And that, unless I've forgotten something important, I think should pretty much be it. Participants can now see your application. What does that mean? Okay, I think that should pretty much be our factorial. Let's try it. 3 factorial is 6. Okay, good, that's right. Oh, it looks like it's finally working. Not quite. It's very easy to write a recursive function like that in C. Turns out it's a little bit trickier in assembly, in Mips, but it's still quite doable at a, fairly reasonable 70-ish lines of code, including all the blank lines and stuff like that. Okay, that's pretty much the end of our factorial example there. Does anyone have any questions about factorial? I'll field those questions for a few minutes. We'll run our Kahoot, and then we'll probably end up wrapping things up pretty much, since this factorial example ended up taking quite a while, but hopefully we've derived some amount of education from this, because I imagine this would probably be at least reasonably useful in your assignment 1s, where you're going to be doing similar sorts of stuff. So questions. Functionally, can you use any register, or do you have to use A0 and B0? So functionally, there are no rules. Like in a pirate's world, there really are no, there's nothing stopping you from, what are pirates not allowed to do again? Like, I don't know, getting drunk on an island. No, they're allowed to do that, aren't they? Right? But they're not being stopped from doing it, but it's the pirate's code that everyone follows and needs to abide by. Hijack a ship. There you go. There's nothing stopping them from hijacking a ship, but everyone will be really upset if they do. That's Mips calling conventions. We are all trying to agree on a certain way to do things. And you'll probably upset other people's code if you start not following those conventions, including the provided code for you in the first assignment. The first assignment code follows those rules, and therefore is expecting things to happen a certain way, being the Mips calling conventions. Can you explain what the stack is again? I can briefly look at our diagram here again, which I've lost over here. Right, so we know we have our text segment, it lives somewhere down here. We have our data segment, it lives somewhere up here. And we have our stack that lives way up here at the top. And the stack is just a convenient place for us to store things for our functions in memory, where essentially the main way of allocating things on a stack, at least as far as we're concerned, is we just subtract 4 from this stack pointer register. So it's now pointing a little bit lower, which is sort of analogous to growing this area of memory, this stack. And then we stick our value in that like gap between where it was and where it is now. That's like our spot where we can store some values. And when we're sort of finishing our function, we put the stack pointer back where it was before by adding back to it. We subtract to allocate because the memory is sort of like getting higher as we go higher, and the stack grows downwards like that. So we subtract a bit, store our thing there, do a bunch of stuff, probably take our value back out or do whatever else, and then move the stack pointer up a little bit again to counteract that. Is that the data text stack located in RAM? Yes, correct. Absolutely. I think, no, I didn't write RAM at the bottom, but yes, correct. I'm guessing you can't add variables to data unless you write it in your program. You adding variables to data. So we have, there's certain senses of data. There's sort of like data that you define in the code of your program, which says when my program starts, I want there to be a string over here. In the assignment, you'll find that there's also things in data that say when the program starts, I want there to be this global variable right here, and you can then use that. But you can also grow the data segment dynamically, but I think that's what you're adding, what you're saying here. You need to specifically do that in your program. And the way you do that is with a special system call, which we won't use in this course, called sbark. Extend the data segment by adding some bytes, which is literally how malloc is implemented. So malloc uses the data segment using this sbark, also another system call that's not listed here called bark, to allocate and deallocate, malloc and free and stuff like that. Cool. Any other questions? That's not growing the data section though, is it? It's growing the heap. The heap is like, so the data section is sort of, you can call it, different people may call it different things. Some may say that the data section is the like global data plus the heap. Some may call the global data section the data section and the heap comes right after it. Yeah, as Abram says, I would say the heap is a dynamic part of the data section. There's like your static data, which you define over here. And then there's your growable data section, which we emphatically call the heap. The frame uses commenting stuff. That's a really good point. How long have I got? We're running out of time, but I'll try and really quickly. What'll I do? Let me go. Unity. Don't want to go to Snake Solutions. Let's just go to files, copy. Okay, let's have a look at snake.s and I'll quickly explain what it's doing. Here, so let's look at an example function over here, like one of the provided ones, just to explain what these comments here mean. If we look at set snake, and let me actually cd blah, 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 not solutions files ln, so we can look at snake c as well. What are we looking at here? Set snake, right? So set snake just does a couple little things here, a couple little lines, and essentially what these comments are saying is it takes 3 arguments: int row, int col, int body piece, and they're meant to come in A0, A1, and A2. It returns void, right? Which if it does return something, usually you'll say where it returns it in, which should usually just be v0. So for example, it returns v0 int for this function down here. What else does it say? We're looking at sense snake. It also says the frame. This is the things that you store on the stack. So you can see that this stores RA, S0, and S1. So that's its stack frame. And then it'll restore them back at the end here as well. It tells you which registers it uses. So it uses those registers that it stores on the stack. It uses the argument registers. It also uses T0 for something, just to help you keep track of what it's doing. It also clobbers T0. So again, this is not for you to use as a guarantee, where it's like, I can use T1, T2, and T3, assume it doesn't destroy them because this is what the clobbers thing says here. It says it only destroys the value of T0. It's more of like if something's broken and you're trying to debug stuff, this is a handy little bit of documentation for you, but you can't make assumptions based off that. It also tells you where it stores local variables. So for example, it immediately puts the arguments row and col into S0 and S1. So it tells you that in locals here. And then the structure just tells you basically the labels. It says there's a prologue where it sets up the stack frame. There's an epilogue where it tears down the stack frame and returns. And then there's just the body here because there's no extra labels. In a slightly more complicated function, say for example, this one with a for loop, it'll say there's a there's like the for I loop, there's the for j loop, and then there's some stuff in there, and then the for j end and the for I end. So it's sort of telling you what labels there are, and you can use a bit of indentation to try and display how the different blocks are interacting, because you never want to indent your assembly code in or out based on the blocks. It's a terrible idea. Please don't do it. Okay. This course had an implement malloc assignment once upon a time. It did indeed. Blah, blah. That makes sense. Great. Awesome. Cool to hear. All right. Any other questions before? I'm sure Hayes and Juliana are just dying to run their Kahoot at this point. Apologies again for sort of running way longer than we're expecting, but again, hopefully I respectfully hope that this ended up being useful in some manner, and hopefully we're not too completely exhausted after a lecture and this afterwards. So cool. Actually really helpful. Thanks. Okay, good. Nice to hear that. Is there a specific order we must complete the functions in? Complete it in whichever order you want to. The suggestion on the course website says that you may find it easier to do the smaller functions first. I think when I implemented the assignment, I did init snake first because it was quite small. I think I did init snake, then I think I did update apple, then I think I did main, then I think I did move snake and array, then move snake and grid, and left the biggest one, update snake, till last. You can do it in whichever order you want, but that's how I did it. And you may find it easier to do the smaller ones first. Cool. Awesome. I think that's probably it for our questions. Hayes would like you to fill in the ARC form here. And I guess we're having a Kahoot. So Hayes, do you want to take over then?
Cool. All right, thanks, Zac. I'm sure everyone really appreciated that. That was insane. That was like a lecture. Okay, so on the left, I put a Word doc just for you guys in case you want to scan with your phone. But yeah, link is also in the chat. And we'll wait for everyone to come into the Kahoot. All right, let me share my audio. Hold on.
Ooh, also, Hayes, how should students get the code from this?
From this one, you can send it to me directly, or you can post in the events.
Okay, cool. So you'll find a way to distribute that across to students?
Yep.
Okay, cool.
You can leave that with me. Also, just in the interest of time, we won't have workshop time to work through the challenge problem. So on the Facebook event, I've posted a Google Drive link for the challenge problem, and also in the Discord hash events channel in the CSESoc Discord, there's a zip file containing the question. So you just have to translate the C problem into Mips, and there's a starter code and also a solution with an explanation in the comments. And big thanks to Vivian, who was able to work it out and get it ready for you guys. So I'll give you guys 1 more minute to join the Kahoot. See, we only have 38. Okay, last call. I think like the numbers have plateaued here. So the first few questions go through a bit of bitwise operations revision as well. So if you have a pen and paper, that's really handy for those starter questions, and then it will move.
They're actually towards the end now.
Oh, really?
Yeah.
Okay, cool. Also, first place will get 1 diamond in the Minecraft CSESoc server. So if you do win, PM me on Discord and I'll get that sorted. But we'll start now. And I'll zoom this out. So for the first question, convert 420 to a hexadecimal. Ooh, very nice. Good job. Okay, Studex coming first. Very nice. Second question. I won't tell you what that sign means, but it's one of the bitwise operators. That's a clue. Yeah, the order didn't change, but that's okay. Nice. So this operator is an XOR. So that means that if it's a 1, 1, it becomes 0. If it's a 0, 1 or 1, 0 here, then it will become a 1. And if it's a 0, 0, it remains 0. And once you convert that to hexadecimal, you get B3D9. Cool. Any questions? Oh, I should have checked that. Cool. What is 2's complement used for? Very nice. So 2's complement is when you negate all the bits and then +1 to it. And that's used to calculate the negative value of the decimal value. Now onto some Mips questions. What is the difference between .ASCII and .ASCIIs? Ooh, nice. Everyone got it right. Right, Newt So Scoot still coming in first, with Ryan close behind. Oh, if you can't see that properly, the memory starts at 0x10000000.
Ooh.
Yeah, you might have to explain this one.
Okay. Do you want to show the media again? Okay, cool. So what is the value of the bytes stored at memory 100D? So if it starts at 1,000, whatever it is, then the first sum word is just saying dot word 4, which is a 4-byte value starting with the value 4. So that should take 0, 1, 2, 3, like those addresses. Some space will be just 4 bytes of uninitialized space. So that should take up 4, 5, 6, 7, those addresses. And then we have a .ASCII Z where each character should be a single byte. So what are we at? We're at 0, 1, 2, 3, 4, 5, 6, 7. 8 should be 8. B is 9. C is A, hexadecimal A. D is B. E is C, and F is finally D. So you get that 1000D finally at that F character. A bit tricky though.
Cool. All right. Thank you, Zach. All right. Next question. On Chinmay rose to the top, with Ryan still in second place. So what are the $A registers used for? Nice. So as Zach explained earlier, $A's are used to like pass arguments into functions. So that would be for functions and subroutines. Cool. Next question. Oh, and Ryan rose to the top. Similar question. What are the $T registers used for? Nice. No one got it wrong. It looks like the positions haven't changed. So next question is, how many bytes does load word read on a Mips 32 processor? Nice. Yeah, it is 4. Okay, Ryan's still in the lead. Next is a true or false question. Temporary registers are preserved across function calls. Nice. So as Zach was saying, it's like the pirate's code. Like, there's no guarantee that the T registers will remain the same after a function is finished, because that function could have altered it. Okay, not much change in the top three. Next question is, which register do we use to pass the syscall number? Yep, it's $V0. So $V0 is the argument that you give syscall to print out whether it's like a string or a char, or to read in an integer. Oh, and Newt so Goot goes back to second. So a very similar question, but which register do we use to store the address of the string for syscall? Nice. So A0 is what actually stores the content to be printed. All right, Ryan's still in the lead with 500 points now. Wow. True or false question. Push and pop are real Mips instructions for operating on the stack. Cool, so it is false. They are not real Mips instructions.
It's probably worth noting as well that there are many other architectures, so x86 or ARM, or I think PowerPC might even often do actually have just a single instruction to push a register to the stack and to pop it.
x86 definitely does.
Yeah, x86 most certainly does, which makes it quite easy to just go push RA, push S0, push S1, and then at the end go pop S1, pop S0, pop RA. Unfortunately, we have to do it in those two instructions in Mips with the stack pointer and then the store word and then the stack pointer and then the load word at the end, which is a bit annoying, but only two instructions.
Cool. Oh, also a fun fact. Apparently, LI, load immediate, isn't a real Mips function either, right, Zach?
Yes, correct. It is another pseudo instruction.
It's a combination of LUI and ORI.
In fact, LI is very interesting because it will either expand into one or two instructions. Sometimes it'll only be an ORI, sometimes it'll only be an LUI, and sometimes it'll be both.
I hope everyone gets the next question right.
We have 5 more questions, I think. Oh my God. I should speed then. My bad. I bet you guys are just memeing. So which of these registers can we not use in an add instruction? Zach, I might have to call on you to explain this one.
This is a bit of a, I don't blame the blue ones here for this being a bit of a strangely worded question, maybe, in that we're not really taught so much that the PC or program counter is like a register like the rest. When you're talking about the actual CPU, like the actual, rock that's doing all the thinking, it does have a program counter register, which basically is just a little register saying which instruction we're up to. But there's no way to really access that like the other registers. Like we can't say $PC or anything. So it's a bit weird to call it a register in this scenario, since it's not like the other registers, but it still is, a register in terms of the CPU. The interesting thing about the 0 register is that if we tried to add, say, T0 and T1 together in that instruction and store it in $0, it would still allow you to do that, and it would still run, but it would erase that value that you store into the 0 register. So you wouldn't really find that result of the addition, which is where I think those blue answers there are coming from. But yeah, that's why you can't access the PC register, so you can't do it at all. It won't even compile your code, let alone try and run it. So that's where that answer is coming from, I imagine.
Thanks, Zac. On to the next question. Oh, Jesse is second and Kay in third, but it looks like Ryan's still 1,000 points ahead of everyone. Next question, what values will be stored in the low and high registers? Ten seconds remaining. I think around half of you still need to submit an answer. Nice. So if we go back to the code, the first line in main, it loads 42 into T0, and then it loads 8 into T1, and then it adds those two together to get 50 into T0. And then in LI T2 4, we load the value 4 into T2, and then we divide TO, which is value of 50, by 4. So what the division instruction does is that it loads the quotient into low and then the remainder into high. So 50 divided by 4 is 12.5, but we take the integer, so 12. And then the remainder is 2. So that's why low is 12 and high is 2.
Something I'd also like to just come in with for a second here is I'm seeing there's a lot of like uncertainty as well in the answers here. Very likely because we haven't really covered this kind of division with the low and high registers properly in 1521 up till this point. So if you're seeing this and going, what, I was meant to know this, I didn't know about that, don't worry, like that, we haven't really gone through this properly. But usually we use our division instructions, and also you'd find the multiplication instructions as well do a similar thing using 3 registers, where we say, if you do div, say T1, T0, T2, then it'll just divide it and store the value in the T1 register. Or we could use the remainder instruction like T1, T0, T2, and it'll do T0 mod T2 and store the remainder in T1. It's more of a different way of achieving things. And yeah, don't be worried if you feel like you haven't really seen this and anything like that. But yeah, that's where your answer comes from, correct?
Okay, second last question. Oh, Kay moved up to second. How many bytes does this struct take up? Cool. So if we go back to the struct, we have 2 integers, which is each 4 bytes. We have 2 string of chars, each of them 20 chars long, and one char takes up 1 byte. So we have 20 bytes in total for each array. And then a double takes up 8 bytes. So altogether it's 4 plus 20 plus 20 plus 4 plus 8, which is 56.
Also, another thing worth noting here is that very nicely in this example, there's no elements of padding or alignment, which can really mess with your struct sizes. I imagine it's probably been specifically created to avoid padding and alignment and these weird things. So sometimes you may sort of add up all the bytes and be like, wait, it's taking up more space than what I added it up to be. And if you're interested in exactly why it sometimes takes up more space like that, then yeah, the things you're looking for are padding and alignment.
Okay, last question. Ryan still first. Kay still coming in second. IEEE 754 single precision floats allocate how many bits to the mantissa? Very nice. Mantissa is the part after the decimal place, right? Right there.
Yeah. It's your fraction part. Mantissa is often called the fraction in many places. So the people who marked 8, you're probably thinking of the exponent, which is 8 bits.
Cool. And
52 is the size of the mantissa for double precision floats.
Yeah. Indeed.
Cool. So that brings us to the end of the Kahoot. In third place, who only got 1 question wrong, is Chinmay. And second place, who got 2 questions wrong, is Jesse. And first place, who got everything right, was Ryan. So I think it's Ryan Burley in the Zoom chat. If you can message me on Discord and I'll get your prize sorted. Cool. And
claim your 1 diamond.
Yeah. That brings us to the end of the Kahoot revision. Not Kahoot revision, the Demipstifying Mips revision session. But we do have a challenge problem for you guys to do. And it's been posted on the Facebook event and also in the Discord events channel. You can download the whole package there. You just have to convert this C program into Mips. It has starter code and it also has a solution there with explanation in the comments. Other than that, that's it. Thanks for joining us. Thank you, especially to Zac, who spent a lot of time preparing for this talk. So yeah, we'll send a feedback form into the Facebook event later tonight. Thanks, everyone.